A very good morning to all for the Day 5 webinar organized by Varadasan University, Entrepreneurship, Innovation and Career Hub. And myself, Tyagarajan, working as Assistant Professor in Department of Computer Science, Central University of Tamil Nadu, Thiruvarur. And today's topic of discussion is current trends, an open research problem in Internet of Things. Before we proceed, we'll just look at what are the four topics which have been covered in the past 4 days. Day 1, we discussed extensively on the introduction of Internet of Things through many examples. On the day 2, we discussed on IoT architecture, the characteristics, and each and every component of architecture in detail. Next, we discussed about how this analytics and visualization and cloud computing plays the role in IoT. Yesterday, we had elaborate discussion on networking and Internet of Things. Today, we're going to see current trends and open research problem in IoT. Before we proceed into today's session, we will just have a quick recap of what we done on yesterday's webinar. Yesterday, we discussed the architecture of how these IoT devices are being communicated with the application server. And we also discussed about what are the various networks available, client server architecture working. We had a discussion briefly on LAN, WAN, MANET, and how this internet protocol works. We also had a discussion on how this IoT protocol works. There are many different IoT protocols available. Among that, we had a brief discussion for about 10 of the IoT protocols. And we also compared these IoT protocols and various parameters. And we also had a discussion on how to choose which IoT protocol is best. Is there any best IoT protocol, or it depends on the application? We just had a discussion on those. With this, we winded off yesterday's session, and today we're going to see the current trends. Before that, we have been talking that IoT device are a smart object. So we will see what is smart here. Previously, before this introduction of networking, we say what is smart. Smart, do you think it's something who thinks it's smart? Or somebody who can compute, can we call them as a smart? That is what the older definition of smart. Someone who can think and can able to act on, put some computation thinking on it, then we can call that device as a smart. Or now, how this smart has changed, it's that a smart is nothing one which can able to communicate over the network. Whenever we say a device is communicated over the network, and can able to do some computational thing, then we can call it as a smart device. That's what the below 4 picture given, that one can think, one can communicate, they are not smart. Even the third picture, one who reads many books. Now with this definition, we can't call him as a smart, because if given any query, he will find the answer, of course, by reading books, but then it will take time. But when a person is connected to the internet, that's what depicted in the fourth picture. When he connected to the internet, and if we ask any query, he can give us answer in a matter of seconds. That we call it as a smart working. Of course, reading is a good habit, I'm not denying that, but in terms of the smart device I'm talking about. So many examples of the smart car, smart home, smart cities, smart mobile, and so many things. This is how the smart has been defined here. So why this Internet of Things has been so much of hype in recent years, and of course it is going to be in the near future also. The fundamental thing why this Internet of Things has been a hype nowadays is that we can able to obtain the data from the previously unconnected devices, and we may not think that these devices we can take data. So in past, we might not have even thought that data can be generated from these devices, but IoT introduction has enabled us to collect the data from those devices. That is what all about, and that makes it IoT in double quotes very popular among the researchers. The fundamental objective of Internet of Things is to obtain and analyze data from assets that are previously disconnected from major data processing tools. You might not have thought that these assets or these devices can able to communicate to the internet. And of course, because of that, we might not have also dreamed of the data generated by the devices can be analyzed for the betterment of human life. Since because IoT made these assets able to communicate with other devices through networking, and we can able to process the data generated by the device, these IoT has become so popular because it has done something remarkable, which a human thought it is impossible. That's why this is hot hype now. In traditional IoT architecture, cloud architecture, we have discussed how this IoT has been related with the big data and the cloud. All of the data from the physical assets or from the devices, it transported to the cloud for storage. As I said, IoT device will be able to generate data at, at every second even. So imagine that in a day, how much of data will be generated. Of course, for all this data to be stored, we need a large data server for them to store. For that, we'll have a cloud data storage. So data generated from the IoT devices will somehow need to travel from the IoT device to the cloud for storage. And from that, we can do the analysis. And transfer of data from the sensors to the cloud platform is not effective. As of now, it is not effective and it is time consuming. Of course, I said, for to have a good cloud computing, we need to have an internet of very good speed. If we don't have internet, then we cannot even think of using the cloud computing. So the data generated from the devices, somehow it has to reach to the cloud, and it should be very time effective. We cannot say that it will reach the cloud in 1 hour and then we can do the data analysis in the cloud. No, it is not possible. Moment it's generated from the device, data is generated from the device, it has to seamlessly go to the cloud. That much of internet speed connectivity should be there, and your IoT devices should be connected to that kind of internet. So this is what the thing which we're lacking on. The transfer of data from the devices to the cloud computing is not that effective, and it has been very time consuming. To overcome this problem, we have two new technologies or two new current trends, which is nothing but edge computing and the fog computing. We're going to discuss what is edge computing and fog computing in this session. Why we need edge and fog computing? So the fog and edge computing makes an attempt to collect the data from the device, IoT device, to analyze the data from the IoT device, and to process the data from the IoT device more effectively. The term more effectively is very important. Of course, without edge and fog computing, also we can able to do collection, analysis, and process. But then that will be done at the cloud, and it will take some time for the data to travel from the device to the cloud. And somewhere these edge and cloud computing are lies between the IoT device and the cloud. And then they say or they claim that they can do the effective data collecting, data analyzing, and processing from the IoT devices. That is what is required now. Because anything in this fast world, we need it very quickly. We cannot wait for even few milliseconds. It has to be done very quickly. That too, for the real-time application, the processing has to be, speed has to be really high so that we can able to fetch the data and you can, in real time, we can able to fetch the data and process it. So the fog and edge computing attempts to collect, analyze, and process the data from the assets more effectively than traditional cloud architecture. With this introduction of this fog and edge computing, we need to be able to do all this collect, analysis, and process much efficient and at a very less time than the traditional computing architecture. That is what they need. So these three architecture, fog and edge architecture, has only three objectives, which is very common: to reduce the amount of data sent to the cloud. All the data generated by the IoT device need not be sent to the cloud. We can have a filter there. What are the data need to be sent to the cloud? What not to send to the cloud? That is one objective. And the second objective is that to decrease the network and internet latency. The latency, the term, technical term, computer science, when is defined as whenever we submit a request and when we receive the response, that time interval, summation of the request and the receiving of the response is called as a latency. It says the ultimate objective of edge and fog computing is to decrease the network and internet latency. And of course, the third point is that to improve system response time in a remote mission critical application. I said in real-time application, response from the system should be very fast. To improve the system response in IoT, we need this edge and fog computing. We're going to discuss in detail about the fog computing in Internet of Things. So the fog computing, the term fog computing can also be called as fogging. Fogging, in other words, referred to as fog computing, was coined first in the year 2014 by Cisco, the network giant. That is the one who discussed this fog computing. So it is new. This fog computing is quite new, and this fog and the cloud computing are highly interrelated or interconnected. So analogously, we can map this fog computing to example so that you can easily remember. You know what is fog, right? That will occur in the month of December. So you know that fog is much closer to the earth than the clouds. Clouds will be in the sky, and the fog will be the closer interaction medium with the human beings than the cloud. A similar way in the technical world also, the fog is much closer to the end user. I'm just mapping it to able to make a clear picture and clear understanding for you. Like how fog is near to the user than the clouds. Similarly, this fog computing also, the fog is very close to the end user, and it brings the cloud capabilities to the ground. What I'm trying to say is that there will be a cloud, and this is the end user, and somewhere we will have a fog computing here. And this fog computing will be able to bring all the capabilities of the cloud computing to this fog computing. So that all the way the data need not travel from the IoT device to the cloud. In between, if you introduce a layer called fog computing, the data generated by the IoT device can go to the fog computing, and the data gathering, collection, analysis can be done at the fog computing, and it can give a quick results to the end user. Or some other data can be filtered from the fog computing, and only a few data can be sent to the cloud computing for processing if it is really needed to huge processing capacity. So it can be mapped analogous to the fog, earth, and clouds. Maybe the definition we can say, the fog is an extension of a cloud computing that consists of multiple edge nodes directly connected to the physical devices. You can say the fog is an extension of a cloud computing that connect multiple edge nodes. See, cloud computing will have only one cloud. In fog computing, we have multiple edge nodes. We will have multiple fog nodes. These are fog nodes. And they will in turn interact with the IoT devices. I will show you an example so that you can easily understand. I hope from this slide I able to point out the definition of what is fog computing and where it will be located between the IoT device and the cloud. It will be located in between the IoT devices and the cloud. This is the picture of a fog computing. It will give a much clear idea to you. See here, the cloud is a top layer and the bottom layer is nothing but devices. And in between we are trying to introduce a layer that is called fog computing. And you see there are multiple nodes. There are multiple fog computing nodes. And these fog computing nodes will interact from the device and will get the data. If it is needed, will process at the fog node, or if it is needed high processing capacity, it will forward and filter the data to the cloud, whichever is required for the high processing capacity. It's a middle one between the cloud and the devices. Generally, the fog computing edge nodes, all nodes, see here, there are 4 edge nodes. In the fog layer, there are 4 nodes, right? They're called fog edge nodes, called as edge nodes. The edge nodes are physically much closer to the devices if compared to the centralized cloud data centers. As, of course, when it is introduced in the middle, the distance, the data it has to travel from the IoT device to the cloud has been reduced because in between introduce a layer, so the distance the data need to travel from the device to the cloud is reduced, and it will travel only to the edge nodes. And it is very closer to the data centers, and that is why we're able to provide very instant connections. There is a considerable amount of processing power at the edge nodes. Of course, we cannot expect the edge nodes to have the processing capacity as the cloud. We cannot expect that. Cloud has an enormous amount of processing capacity, enormous amount of storage capacity, but that kind of thing cannot be expected from the edge nodes. But then it will have some amount of processing capacity and some amount of storage capacity. Not like cloud, but it will have some amount of processing and storage capacity. The considerable processing power of the edge nodes allow us to perform some sort of computation from the data which is generated by the IoT devices. The data is being generated by IoT devices. We can able to perform some amount of processing, whichever can be done at the edge node, that can be done. And we cannot, some 10 data, 1,000 data are generated from the IoT devices. Not all the 1,000 data can be transferred to the cloud computing. We can have some filters. Whichever data is not required, that checking can be done at least in the edge node, so that only the data which is really of useful to the business, that can be forwarded to the cloud computing for further processing. So what it will do is that unnecessary data will be filtered. We can do that filtration in the fog nodes. So what will happen unnecessarily if we filter it, then the amount of traffic from the edge nodes to the cloud computing will be reduced, which will improve the latency. Okay, so it will have some amount of edge nodes, will have some amount of processing capacity, and that will help us not to send all the data which is generated from the IoT devices to the cloud. And fog also includes cloudlets, which is very small scale and rather very powerful data center located at the edge of the network. The purpose of this cloudlets is to support resource intensive IoT apps that require low latency. So whenever you introduce this fog computing, the latency, the response time of the request, the processing time of the request will be much less, because most of the process, highly crucial process will be done by the fog, and then only major data will be sent to the cloud. So response from the user will be much quicker. The main difference, if you want to know, between the cloud and the fog is that one thing, cloud is a centralized system. You see, we have only one cloud. Whereas we see a fog, it is a distributed centralized infrastructure. We have the fog nodes distributed, and hence we call it as a distributed fog, decentralized infrastructure. It's a centralized, it is decentralized. That's what the main difference between the cloud and the fog. Fog computing is mediated between the hardware and the remote server. Hardware, I mean here, is nothing but the IoT devices, and the remote server is nothing but the cloud computing platform. It regulates, or it decides what are the information has to be passed from the devices to the cloud server. You can have a filter. For example, if the data is generated from the smartwatch, need not all the data generated from the smartwatch stored in the cloud. If the heartbeat is normal, then those data need not be sent to the cloud because it's very normal. When there is a slight variation, that variation data need to be stored in the cloud. So if you want to restrict the normal data to be stored in the cloud, unnecessarily to be occupying the spaces, and you have to pay for that in the cloud, so you can put a logic in these edge nodes in the fog computing, so that the normal data need not be stored in the cloud, only the abnormal data, quite even small variation of the data can be stored in the cloud. That filtration can be done in the fog computing, and ultimately it will reduce the storage capacity in the cloud, as well as it also reduce the network traffic. In this way, the fog, we can say it is as an intelligent gateway. We can say it as an intelligent gateway that offloads the cloud, enable only to store the more efficient data, so that the cloud can not store the unnecessary data, and it can store only the essential data, and can process the data, essential data, and can analyze the essential data. And one more very important point is that the fog networking is not a separate architecture, it's not a separate entity. This fog networking or fog computing is not a separate entity. In turn, it is not also replacing the cloud computing. What does it do? It rather complements the cloud computing. This fog computing is complementing the fog computing. It's a very important step. One should note that fog networking is not a separate architecture and doesn't replace the cloud computing. In turn, it complements the functionality of the cloud computing by only forwarding the essential data so that it can process and it can be analyzed. The new technology is likely to have this fog computing is likely to have the great impact on the development of IoT. So for now, there's a talk going on that these IoT devices are not suitable for the real time, but the introduction of this fog computing has made it suitable for the real time also. It is going to have a great impact in the development of IoT, as well as the embedded artificial intelligence, and as well as for the 5G solutions. And whatever application that has that demands agility in the sense that things will change quickly, and the seamless connection with this helpful of introduction of fog computing, we can able to deploy the IoT for the time critical applications. Now we are going to discuss what are the pros, advantages of fog computing. There are many advantages of this introduction of fog computing in the Internet of Things, especially for the real-time analytics. And we're going to discuss that in later. The introduction of fog computing enables us to have the low latency. Low latency in the sense the response time has been increased a lot. So as I said, fog is geographically closer to the user, and hence can able to provide very quick responses. The delay has been reduced because of introduction of this fog computing in between the IoT device and the cloud platform. And there is no problem with the bandwidth. Why? Because this introduction of fog computing avoid us to gather the information and bombard into the cloud computing. Since it is a decentralized system, the pieces of information from the IoT devices can be aggregated at different decentralized system. We don't have this fog computing, all the data generated by these IoT devices will be bombarded to the cloud at once. That will cause the bandwidth issue. This has eradicated the bandwidth issue because it's a decentralized system, and hence the piece of information are aggregated at different points in the decentralized system. And instead of sending them together, it will change via many channels to the cloud computing. That will avoid the bandwidth problem. Very, very important point. And also, we will not experience the loss of connection problem. This fog computing is not there. Imagine there will be only IoT device and there will be cloud. And if the connection between the IoT device and the cloud is gone, then we will not able to send the data because it's a centralized system. But with the introduction of this edge nodes in the fog computing, you will not able to have connection loss. Even if it's connection loss, it will be only to the one edge nodes in the fog computing. Because there are multiple nodes, edge nodes are connected to the cloud. We will not have our loss of connections is minimal. You can say it is also impossible. And we can also have or able to provide high security because the data collected from the devices are processed at a huge number of roads in a distributed system. We can able to provide high security with the help of this fog computing. We can able to provide improved user experience. Improved user experience in the term, we can able to provide them with quick instance of output to the user. Instant responses and don't downtimes that will also be satisfying the user. And one more last advantage of this introduction of fog computing is power efficiency. The node runs power efficient protocol. The edge nodes in the fog computing will always run on the power efficient protocol, such as Bluetooth, Zigbee, or Z-Wave, which will not use that much power. So these are the very, very important advantages of introduction of fog computing in the Internet of Things. And if we see, this technology has not introduced any apparent disadvantages. There is no any major disadvantages, but we want to name some of the shortcomings of introduction of fog computing in this IoT. We can say it makes the system a little more complicated because we're adding in one more layer. Of course, addition of one more layer will be making the system a little complicated. And it is also resulting in introduction of new nodes. So we can obviously have extra cost involved in introduction of the nodes between the fogs between the IoT device and the cloud. And this fog computing is not as scalable as a cloud. In cloud, very, very important advantage is the scalability. We can scale the processing capacity or the storage capacity at any time to any extent. But that cannot be done in the fog computing. It has a very limited resources. So we cannot done that much scaling as we do in the cloud. So these are the some of the shortcomings. We can say this is not a major thing compared to the advantage. This is not major shortcomings. But if you want to really discuss some of the things, then say these are the things: a more complicated system, additional expenses, and limited scalability. So that is what the importance of the cloud and the fog. So now we're going to have a quick comparison of how this cloud and the fog can be compared. So this has been compared on 9 different features like architecture, communication with devices, data processing, computing capabilities, number of nodes, analysis, latency, connectivity, and security. We see the cloud, as I said, it is a centralized architecture, whereas fog is distributed or decentralized. And in cloud, connection with the device is usually from a quite long distance. Cloud will be somewhere and the device will be somewhere. So data has to travel all along the way from the device to the cloud. So the communication with the device will be from a distance. Whereas fog, it directly connects with the devices. So the distance will be obviously small. And data processing that is take place in the cloud is far from the source of information. Whereas in the fog computing, the data processing will be done very close to the source of information. And if we see the computing capability of the cloud, as I said, it is very, very higher, whereas fog computing capability is very low. The number of nodes in the cloud, I can say, we cannot say as much high as fog. So number of nodes in the cloud is few, whereas fog, we have a number of edge nodes. It's a decentralized system, so it is very large. Number of nodes in the fog is very large. So analysis, we can do long-term analysis in the cloud. We cannot do this very tough analytics process in the fog computing, considering the computing capabilities. And latency, that is the response time is very high in the cloud, whereas fog, the response time is very low. Since it's very located very closer to the devices, the response time from the fog computing will be much more quicker than the cloud computing responses. And for connectivity with the cloud, of course, I said you need internet, and to connect this edge IoT devices to the fog, we need not need internet. We need only some protocols. There is one more advantage. There is no internet, we cannot store it in the cloud. But without internet, also data generated by the IoT devices can be processed, minimal processed by the fog edge nodes. Because it doesn't need internet, it only needs protocols and standards. And security, the cloud computing security does not provide much security to this IoT data, whereas compared to the cloud, fog provides some kind of security mechanisms. These are a quick comparison between the cloud and the fog.